2 plus 6. So the outermost shell, 8 electron configuration when they are linked by chemical bonds. So basically, Lewis tried to explain why bonds are being formed, and his postulate was that because the electron configuration in the valence shell, that is why they are forming chemical bonds, because all of them are not having 8 electrons in their valence shell. All right, let us move on. We will see some examples. For example, in the case of sodium and chloride. So sodium will donate the excess electron because the previous shell of sodium is already complete. Similarly, chlorine will take this electron and it will complete its outermost shell. So sodium chloride is an ionic compound in which sodium has a positive charge. It has lost an electron to chlorine, and chlorine example, sodium chloride, they are losing and gaining electrons. In the second example, they are sharing electrons. Okay, they're not losing and gaining. To clarify this, Lewis gave symbols in which he represented the atom along with the outermost shell and how many electrons it had. For example, for lithium, it has just one electron in the outermost one. For beryllium, it is 2s2, so it has 2 electrons. We will draw 2 dots. Boron will have 3, carbon will have 4, nitrogen will have 5, and so on. We can see until neon comes with an absolutely stable lot of 8 electrons. So this is how we can draw the Lewis symbol. It is very easy. You just need to know how many electrons are there in the outermost orbit of the atom. Now, the significance of the Lewis symbol, it is basically to determine the number of how much short it is of achieving an octet. Now, what was Causal's contribution? He drew attention to a following fact, that highly electronegative halogens and highly electropositive alkali metals are separated by the noble gas. Then he postulated that a negative ion is formed from a halogen atom and a positive ion is formed from alkali metal, which is associated with gain and loss of electron. Along with that, he said that negative and positive ions thus formed, they attain stable noble gas electronic configuration. That is why they are formed. Except helium. Helium is instead of an octet, it has a duplet of electrons. All right. Okay. The negative and positive ions are stabilized by electrostatic attraction. So formation of NaCl or formation of CaF2 or other compounds, we can see that we can just see how sodium is losing an electron and gaining the noble gas configuration electron, and it is achieving the noble gas configuration of argon. So this bond formed as a result of the electrostatic attraction between the positive and negative ions was termed as the electrovalent bond. And electrovalence is thus equal to electrovalence is equal to number of charge on ion. So what electrovalence is? It is the number of charge on the ion. For sodium chloride, electrovalence will be 1 for sodium, 1 for chlorine. Right? Okay. The next is calcium is assigned a positive electrovalence of 2, while chlorine a negative electrovalence of 1. So this was the Cauchy-Lewis theory. Now we'll go to the octet rule. It is nothing. It says that all of them want to achieve a stable octet. Okay. Moving on, we now try to define covalent bond. Okay. So it is a bit interesting how a covalent bond is formed. Langmuir was the scientist who postulated that sharing of electrons, like he abandoned the idea of this cubical arrangement of octet, and he said that electrons can be shared to form octets. So the basic thing is, at any point of time, each atom, each element in the bond formation should have a octet. For example, let's see a Cl2 ka formation. Cl chlorine atom has 7 electrons in its outer shell, each chlorine, and it needs just one. So what happens if this first chlorine takes or shares an atom of the second chlorine, and it also shares one of its own? So sharing is always bilateral. If you do unilateral sharing, it is not sharing, it is basically donating. If you are sharing, the first chlorine will give one, second chlorine give one, and totally we have two electrons which are being shared. So we can see that in the first circle, which I'm drawing with the brown, how many electrons are there with the chlorine? We have 8 electrons. Similarly, let's see the second circle, which I'm drawing with yellow. We again have 8 electrons with the chlorine, the green part being common to both. This means that both chlorines are getting stable noble gas configuration without donating or losing or any electron or gaining any electron. So no charge is being gained. Just by sharing, they are reaching their octet. All right. So let us proceed further, and we can define bonds on the basis of Lewis dot structures. So each bond, okay, one bond, it is formed as a result of electron pair between the atoms. So one bond, one pair. So if two electrons are present, which means one pair is there, it will lead to formation of one bond. Each combining atom contributes at least one electron to the shared pair. So each atom must contribute at least one electron to the shared pair, which is what I said. It cannot be unilateral, it has to be bilateral. The combining atoms attain noble gas configuration as a result of sharing electrons. And in water and carbon tetrachloride, the formation of covalent bond can be represented as, let us see, hydrogen is giving one electron, oxygen is giving one electron, and in total, oxygen is getting one extra. So it is getting a noble gas configuration of 8 electrons. Hydrogen is getting a duplet of 2 electrons. Right. Carbon tetrachloride, carbon has only 4 electrons. It will share all 4 of its electron with chlorine, which needs just one. So you need 4 chlorines because each chlorine will give just one. So carbon needs 4. You need 4 chlorines to complete the carbon's octet, and here we can see the octet has been completed. Again, we move on. When two atoms share one electron pair, they are said to be joined by a single covalent bond. If a number of pair is 1, then one covalent bond is there. If they are joined by 2 pairs, then double bond is present. If 3 pairs are there, triple bond is present. As we can see in the CO2, 4 electrons or 2 pair means a double bond. Similarly, in the other side, there are 4 electron or 2 pairs, and we have another double bond. Let us see an example of a triple bond. Here in N2, we can see that 6 electrons are being shared, which means 3 pairs, which means 3 bonds will be formed. Similarly, in ethyne, we will have a triple bond because 6 electrons are being shared. Let us move forward. Now we'll go to the Lewis representation of simple molecules, which is the Lewis structure. We'll just simply learn a few terms. We'll see how electronegativity works, how charges are being distributed. Right. Let us move forward. The total number of electrons required for writing structures are obtained by adding the valence electrons in the combining atom. So, if we are drawing the CH4 molecule, carbon will be having 4 valence electron and 4 hydrogen will be giving 4 electrons, so total 8. Right, 4 from carbon, 4 from the 4 hydrogen. This is how you first figure out how many number of electrons are there. Now you have to arrange. For anions, each negative charge would mean addition of 1 electron. For cation, each positive charge would mean the subtraction of electron. Right? The number of, for example, in carbonate ion, the 2 negative charges indicate that there are 2 additional electrons than those provided by neutral atoms. What does carbonate mean? Carbonate means, I'll just try to figure out the number of electrons in carbonate, valence electrons. Carbon is there, oxygen is there, and some extra electrons which are giving negative charge are also there. Let's see how much electron carbon gives. A carbon will give 4 valence electron. Each oxygen will give uh, about 6. So total we have 3 oxygen. So into 3, that will be 18. And extra we have a charge of -2, which indicates 2 extra electrons. Total we have 24 valence shell electrons for a carbonate ion, and we can easily check that yes, a carbonate ion is having total of 8, 8, 16, 4, 20, 2, 24. Yeah, 4 valence shell electrons. This is how you have to account for the charges. Like if there is a positive charge in case of NH4 plus ammonium, you will just subtract 1 electron from the total number of valence shell electrons. So if nitrogen gives 5 and each hydrogen gives 1, so it should be a total of 9. But in ammonium ion, we will find 9 minus 1, that is 8, minus 1 because a positive charge is present. Right? You understood this point? Let's move forward. Knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of compound known or guessed intelligently. Okay. It is easy to distribute the total number of electrons as bonded shared pair between the atoms in proportion to total bonds. Right. This is, we'll see while making bonds. Let's move forward to the next rule. In general, the least electronegative atom occupies the central position. Right. Least electronegative atom as in your central atom. Usually the central atom is the least electronegative, except for a few compounds like your H2O and H3, in which the central atom is more electronegative than the peripheral ones. All right, but usually we'll just follow this rule that least electronegative atom occupies the central position. Examples are NF3, CO2, 3, CO3 2 minus, which is carbonate. Right. Next, after accounting for shared pair of electrons for single bonds, the remaining electron pairs are either utilized for multiple bonds or remain as the lone pairs. Right. Basic requirement is that each atom should have a complete octet of electrons. So if a octet is getting completed, then the remaining atoms will be lone pairs. If the octet is still not complete, so you will make multiple bonds to complete the octet. Right. Let us view a few structures based on this rule. First one, we have hydrogen, which is more basically an exception because it has a duplet instead of a octet. Anyways, we move to oxygen and we can see that each oxygen atom is having a octet completed, and a distribution is also very wisely done. Okay, ozone is a bit tricky because we'll try to draw ozone. Let's see how it goes. So ozone, I'm so sorry. Ozone is basically your O3, right? And the total number of electrons, valence shell electrons, is 6 into 3, 18. Okay. Now the thing is, if I draw an oxygen 1, 2, 3, 4, 5, 6, again an oxygen here. Let me draw a bit bigger. So I draw 3 oxygens. Similarly, I'm drawing this structure. See, this for the first oxygen, we have a complete octet. Even for the second oxygen, we have a complete octet. But you see the third one is getting up like extra electrons. It is getting extra electrons. It has how many? 10 electrons, which is not possible. So it is a bit tricky. This is not the correct structure of ozone. We will try to see why. So to distribute 18 electrons as such that every one has an octet complete along with no exception, like not more than 8, what we'll do is we'll assume that one of the oxygen has a positive charge and one of them has a negative charge, right? So if this oxygen has a positive charge and this one has a negative charge, basically the neutral oxygen will just draw normally. It is sharing normally with your this oxygen. And for the oxygen with a negative charge, we will initially put a lone pair electron because it has extra number of your electrons. Okay. Here. Here we can see that your basically what is happening. I'll just show the formation in a stepwise manner. See, this is the first oxygen which we have, and it has 6 electrons. So it will give 2 electrons and bond with the second oxygen. This is done. Now comes the third oxygen. So what happens for the third oxygen is the one which I'm marking with a star, oxygen with the star, it instead of sharing 2 electron pairs from the, because this octet is complete, it does not need any extra electrons. So what it does is it gives these 2 electrons, it shares it with this oxygen. No harm. See, no harm is there. This hash oxygen, when it gets these 2 pairs, it will get a complete octet. And the star oxygen already has a complete octet. So there is no harm in sharing oxygen, the electron pairs like this. It looks something like this. Right? It looks something like this. Here, because the star oxygen is electron, so it will have a positive charge. And because the hash oxygen is accepting this pair of electron, it will have a negative charge. It looks something like this. These 2 pairs of electrons are shared between both, which actually belong to the star oxygen. The hash is basically a parasite here. This is called a donation of lone pair and coordinate bond. Here it is called a coordinate bond. Okay, let's move forward. Similarly, we have NF3, which is easy to decipher. Carbonate, I told you. Negative charges which are present on 2 ox and HNO3. All of these are easy to decipher. This coordinate bond is different. Now we'll see formal charge, what a formal charge means. Lewis dot structure do not represent the actual shape. The net charge is possessed by an ion as a whole, not a particular atom. However, it is feasible to assign a charge on each atom. How to assign a charge on each atom? There is a formula, and this is the formula for calculating formal charge. Formal charge on an atom is total number of valence electrons in the atom, total number of non-bonding or lone pair electrons you have to subtract, and you have to subtract total number of shared electron and divided by 2. Right. Here they have again taken the example of ozone. For oxygen number 2, I'm so sorry, oxygen number 2, the total this thing is 6 valence shell, and lone pair electrons are 4, and there are 4 bond pair electrons which are divided by 2, so it has a 0 charge. Similarly, the one marked as 1, it has +1, and a one marked as -1 charge, which we already had seen in the previous. This thing now we'll go on and see the limitations of octet rule. All right. Before that, generally the lowest energy structure is the one with the smallest formal charge on atoms. Lowest energy structure, smallest not an ionic character right now. Okay, limitations of the octet rule. What are the limitations? Firstly, there are some atoms which have incomplete octet. For example, LiCl, BeH2, and BCl3. Although chlorine, hydrogen, and again chlorine, hydrogens, and chlorines are having phosphorus,
Recording in progress.
sulfur. Here in SF6 there are 12 electrons, in PF5 10 electrons, and in H2SO4 there are 12 electrons around the sulfur atom. Again, we clearly discussed some drawbacks. There are exceptions. It is clear that octet rule is based upon chemical inertness of noble gases. However, some noble gases form compounds like xenon, krypton. All right. Next is, this theory does not account for shape of molecules. This does not explain the stability of molecules, and silent about the energy. These are some drawbacks of this thing, Lewis theory. Now we have an ionic bond. Let's finish ionic bond easily. For defining an ionic bond, we have an electron gain enthalpy and ionization enthalpy, right? Electron gain enthalpy is defined for an anion, which means A accepts electron and becomes A minus with a release of some energy. This energy is the electron gain enthalpy. Now, if an atom gains an electron, it releases some energy. This energy is known as electron gain enthalpy. When an atom loses electron and becomes a positive cation, some energy needs to be supplied. This is your ionization and enthalpy. To ionize an atom, you need an ionization enthalpy. To, create an ion, you need electron gain enthalpy, and the amount of these energies basically determine what kind of ionic compound is feasible or not, right? Okay, let's move ahead. Ionic bonds will be formed more easily between elements with comparatively low ionic bonds. All right, let's move on and let's see what a lattice enthalpy is. Lattice enthalpy is energy required to completely separate 1 mole of solid ionic compound into gaseous ions. NaCl is a solid. If you convert NaCl solid to NaCl gas, in which both ions are separated from each other, that is known as the lattice enthalpy. We can go to the reverse also. If we have a gas of ions and we condense it into a solid crystalline structure, some energy will be released. That is the enthalpy of lattice. Right? This was
Recording in progress.
Bond length, right? Van der Waals radius is usually higher vitals of different bonding electron pairs around the central atom in a molecule or complex ion. It is expressed in degree, which can be experimentally determined by spectroscopic methods. So, for example, in H2O, the bond angle between HOH bond is 104.5, and there are various parameters that determine your bond angle. Moving ahead, bond enthalpy is defined as the energy required to break 1 mole of bonds in a particular type between two atoms in a gaseous state. Break the hydrogen-hydrogen bond, we need to supply some energy. This is the bond enthalpy. Sorry, enthalpy is usually represented by H. Delta. It is important that a larger the bond dissociation enthalpy, stronger will be the bond. So if the bond is strong, therefore to break the bond, you will have to give more energy, which is really simple to understand. Okay. And we already know that double bonds are more stable than single bonds, and triple bonds are the more of triple bond, then double bond, then single bond. Then to define average bond enthalpy is like the first bond energy is always more, and the second one is usually less than the first one. The average of both is average bond enthalpy. Next, we have a bond order. Bond order is the number of bonds. See, in H2 molecule, it has 1 bonds. In an O2 molecule, it has 2 bonds, so bond order will be 2. N2 molecules, 3 electron pairs are there, so 3 bonds will be. Okay. So we were talking about resonance and resonance structures. It is often observed that a single Lewis structure is inadequate for representation of a molecule in conformity with its experimentally determined parameters. Resonance explains why ozone has same bond length. Although we can see that one of them is a single bond and one of them is a double bond, but in ozone we find this intermediate kind of structure in which your bond lengths are identical because one of these double bonds electron, they are shared in between both the bonds. That is why the bond length becomes identical. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, number of structures with similar energy positions of nuclei bonding and non-bonding pair of electrons are taken, which describes the molecule accurately. This is called a resonance hybrid. Other examples of resonance are carbonate ion and carbon dioxide molecule. For resonance, you need a charge. You need either charge, you need double bonds, alternate double bonds or double bonds with single bonds and charges, something like that. All right. Okay. In general, resonance stabilizes the molecule as energy of resonance hybrid is less than the energy of any single canonical structure. Then resonance averages the bond characteristics as whole. It has averaged the bond energies, it has averaged the bond length, it has averaged the bond order. Everything has been averaged for resonance. So there is some misconception. The canonical forms have no real existence. Okay. This is, you should remember that a canonical form is not existing as whole. Only a resonance hybrid is there. Molecule does not exist for a certain fraction of time in one. It is not like the molecule exists for 1/3 of the time in one canonical form and 1/3 of the time in another, something like. It always exists as a resonance hybrid only. Just to explain the formation of resonance hybrid, canonical forms are drawn. There is no equilibrium between canonical forms. Okay, there is no equilibrium between canonical forms. Only resonance hybrid is existing. No canonical forms are existing. The molecule has a single structure, which is resonance hybrid. Canonical forms cannot be depicted by a single Lewis structure. That's why canonical forms are required. So this was all about your resonance. Next, we move on to polarity of bonds. Polarity of bonds is basically, I was talking about electronegativity. Right. What is electronegativity? Electronegativity is the characteristic of an element to, attract a shared pair of electrons towards itself. In a covalent bond, although both the elements, both the atoms give one electron each, they share one electron for a single bond, but the pair of electron is usually shifted towards one element, which is more electronegative. This is a tendency, this is a kind of a competition between the elements. The ones which are more electronegative will tend to attract towards themselves. All right. And the ones which are less electronegative tend to give away. So basically the electron pairs, although it is like in a constant motion, but they mostly exist near the more electronegative atom, and they slightly exist near your less electronegative atom, which gives the electronegative atom a partial negative charge and the electropositive atom a partial positive charge. Right. Okay. So something which I can explain, an example which I can take for you guys is, let us take H2O. H2O. So the hydrogen is less electronegative, oxygen is more electronegative. So the shared electron pair tends to move towards oxygen and the dipole moment is towards oxygen, right? Oxygen has a partial negative, hydrogen has a partial positive charge. Okay, when covalent bond is formed between two similar atoms, electron pair is equally shared. It is between the nucleus. But when two different heteromolecule is there, HF, shared electron pair gets displaced more towards the electronegative atom. That was the explanation for your polarization. As a result of polarization, molecule possess a dipole moment, right? Which can be defined as the magnitude of charge and the distance between the centers of positive and negative charge. So it is designated by mu, and there is a formula also, charge into distance, right? Dipole moment is a dBi is the unit, and 1 dBi is this much of Coulomb meters. Okay, for HF, this is the dipole moment ka direction, and this is how a dipole moment is expressed, right? This arrow symbolizes the direction of shift of electron density. Note that the direction of the crossed arrow is opposite to the conventional direction of dipole moment vector. Usually, the dipole moment vector in physics is towards positive, but in chemistry, we draw a crossed arrow which is towards the negative. Okay, move on. We move on. Okay, Peter Debye was the one who discovered this dipole moment. He worked on it, so Debye, a unit was named after him. Next, we move on to the polyatomic molecules which have more than one bonds in case as in case of H2O. We saw that there are two dipole moments. The net sum will be addition of both dipole moments in a vector form, which will give a single large dipole moment. The OH bonds are oriented as at an angle of this. Net dipole moment is this, resultant a moment of two OH bonds, right? Similarly, for BeF2, dipole moment is 0 because they are in opposite direction. So BF3, they are in, it is almost 0, right? Now let us study NH3 and NF3. So for NH3 and NF3, we have to remember one small thing. NH3 is something like, and the dipole moments are towards, there is a lone pair also. Now NF3, dipole moments are towards your fluorine. See, these two arrows are different direction, but these are in the same direction. So this results in decrease. So NH3 has a larger dipole moment, right? Okay. This was basically today's topic. We will start with VSEPR theory in the next class. Let us move on to the questions. We will try to solve questions related to today's topic. Okay. Tomorrow we'll do VSEPR theory, molecular orbital theory, valence bond theory, and all. All right. Sorry. Just for the sake of doing, we'll just do the summary also after we are done here. Let us try to solve some previous questions. First question says the bond dissociation energy of BF3 is this, whereas in CF4 is less. Correct for higher BF bond dissociation energy. Okay, so we will, this is not a question. We'll go to next question. This is also not our question. Question number 2. Question number 3 is molecular orbital theory. Leave it. Okay, question number 4 we can solve. Which of the following has the small bond? This is also molecular orbital theory. Question number 5, 6. Let us solve question number 6. Based on lattice energy and other consideration, which of the following alkali metal chlorides is expected to have the highest melting point? So lattice energy says stronger the lattice, higher melting point. All right. So a lattice will be strong. I'll just explain this concept in a short manner. I'll just try to draw a lattice. This is a lattice. We will draw cations and anions. So suppose this is cation and this is anion. Again, we draw a cation and we draw a anion. We draw an anion. We draw a cation. We draw an anion. We draw a cation. You can see what kind of structure is being formed in this. Here, the sizes of cations and anions are like they are really different. Let us move to one more structure in which the sizes are same. This is the cation. This is the anion. This is the cation. This is the anion. This is the anion. This is the cation. This is the anion. This is the cation. Tell me which has a more closer packing. Definitely your second one is more closely, densely packed, which means the lattice is stronger in the right hand side wala part, or the second. The smallest, the smaller the cation, the more stable the atom. For reason for small cations to, see here cation is large, here cation is small. Small cations tend to distort the anion. What does distort means? See, the anion, instead of being in a big circle, it usually looks something like this. Okay, it is being distorted. Because it is being distorted, there is a polarity which is being generated, and polarity means stability is increasing. Because of this distortion, polarity is being generated and stability is being increased. So the smaller the cation, the denser the charge, positive charge on it, the more it will be able to polarize. Right now we can see that lithium is the smallest cation, but LiCl is a covalent compound. So melting point is drastically low. Covalent compounds have very low melting point, okay? Because the bond is very, kind of weak. So after lithium, we have sodium chloride. Answer will be your sodium chloride, uh, without any doubt. Okay. Now, dipole moment question we can solve. This is a 10th number question. Compound of xenon with a zero dipole moment is. We will try to draw Lewis dot structures and try to see how each compound looks. Xenon as whole is a noble gas and it has a complete octet. We'll try to draw Lewis dot structures and take a little bit help of the kinds of uh, we'll give it some reasoning. Okay, let's see. XeO3. For XeO3, you need to have this kind of structure, right? This is XeO3, and this kind of the lone pair will be on top because it needs to be as farther away from the bond pairs. So here we can see that there is a kind of there is a kind of polarity. XeF3 is not the answer. XeO3. Next, XeO2. XeO2 is like this. So we can see that if we add these up, there will be one dipole moment here and a large dipole moment towards oxygen, which gives us a kind of dipole moment like this. This is also not the answer because dipole moment needs to be zero. So we have successfully eliminated XeO3 and XeO2. We move on to the fourth option. We know the answer is XeF4, but we move on to the fourth option. XeOF4. Okay, still there is a lone pair remaining. How it should we arrange it? See, we arrange it in a form that this is XEF, this is XEF4. Okay. So what is happening is this 4Fs are in one plane with the xenon. The oxygen is projecting out of the plane and the lone pair is projecting out of the plane too. So it is kind of the plane is like this. We have 4 fluorine at the corners, xenon in the center, oxygen is like this, lone pair is like this. Sorry. Yeah. So I was at, yeah. The 4 dipole moments will cancel each other, which means the dipole moments in this plane. So these as we just saw, one dipole moment here, one dipole moment here, these two cancel each other. All the 4 fluorine dipole moments cancel each other. So net dipole moment is equal to 0. So our answer is XeF4. Why? Because it has a square planar structure. It has a square planar structure, 2 lone pairs directing from it, lone and Xe at the center. So dipole moment is 0. Let us move on to the next question. Which of the following has maximum number of lone pairs associated with xenon? Let us calculate the lone pairs XeO3. Oh, so for Xe, you just need to satisfy the octet of the opposite atom. So satisfy the octet of each oxygen, we get these 3 bond and 1 is remaining lone pair. XeF4, we have 2 lone pairs. XeF6, we still have 1 lone pair remaining. XeF2, three. Answer will be XeF2 because XeF2 has the maximum number of lone pairs because it has the least number of bond pair, and xenon has kind of like 8 octet electrons. Still, we just simply see that XeF2 has the maximum number of lone pairs. Again, we get a molecule with the lowest dipole moment. Here, we can apply some kind of logic. Lowest dipole moment they have asked. For each of the other 3 molecules, there is a chlorine, there is at least 1 chlorine and 1 hydrogen. Okay. Except CCl4. CCl4 is having 4 bonds purely with chlorine, and therefore the dipole moments will cancel each other out. It has a 0 dipole moment. Answer is easy to identify with a bit of reasoning. Answer will be CCl4. All right. Calcium carbide, the types of bonds. Calcium carbide is CaC2. So there are 2 pi bonds between the 2 carbons, 1 sigma bond. 2 pi and 1 sigma is the answer. Hybridization we have not studied. Bond angle we can answer. Smallest bond angle, PCl3. What is happening? So PCl3 has something like lots of spaces. Phosphorus is a large molecule. Then comes nitrogen. We can see the repulsion between chlorine and NCl3 is really high. Really high, because nitrogen is a small atom, phosphorus is a very large atom. Similarly, if we take arsenic, it will be even larger. No repulsion at all. They can exist peacefully. Getting these points in mind, we will just write that NCl3 has the largest, PCl3, then ACCl3, then SPCl3. Okay. Structures we'll do next time. Diamagnetic, paramagnetic next time. Wrong statement. Okay. NOCl and NO2 minus are not isoelectronic. This is correct. O3 molecule is bent. It is correct. Ozone is a violet black in solid state. It is correct. Ozone is a diamagnetic gas. I think no, nothing is wrong here. So all are correct only. All are correct. This is a wrong question. Wrong question. Okay. Right. Stability we'll do tomorrow. Existence tomorrow. Bond distance, dipole moment, percentage ionic character. Percentage ionic character we'll do tomorrow. Which of the following ionization process the bond energy has increased in magnetic behavior? Okay, tomorrow. Then paramagnetic, diamagnetic, it will come tomorrow only. Catenation tendency of carbon, silicon. Catenation is forming bonds with itself. Carbon has the highest catenation tendency. Bond energies will be, so carbon bond energy will always be higher, because carbon are closer. Silicon, it is something like very farther, and germanium is like really further. So bond energy will be more when atoms or nuclei are closer to each other. So carbon bond energy will be the most. Hence option 2 will be the answer. Then oxidation state, this we can SO3 2 minus SO S2O4 2 minus S2O6 2 minus. Oxidation state we have to calculate. For SO3 2 minus, this is SO3 2 minus, right? Oxidation state is simply, if we calculate from positive negative charges, it is +4. For S2O4 2 minus, it is 5 +5. S2O4 2 minus, actually it is +3, because there is a peroxy linkage. This is +4, this is +3, this is +5. So we have something like this. Next, hybridization we'll do tomorrow. Rest of the questions we can do tomorrow.